Welcome back, students. So, in this lecture, we will look at operational amplifier as a black box. We could do this particular class in a variety of ways, but I thought this would be the most interesting way of doing studying analog circuits. So, initially, I would like to expose you to operational amplifier, what operational amplifier as a black box behaves like, and what are the different non-idealities that we see in the operational amplifier, its impact on the circuits. And the main reason for this was there used to be a associated lab in the afternoon, so you could whatever you have learned in the classroom, you get to play with that when you go back to the lab. So we will continue doing that because we found that students really like that approach. Even though you don't have a lab, or many of you who are listening to this on the satellite program, you're not doing any lab, but I will try to show you variety of things which are almost like a lab experiment. Okay, so let's see how that goes. Give us the feedback if this method works better for you. So in today's lecture, as I said earlier, we are going to look at operational amplifier as a black box. Now, what is operational amplifier? So as the name suggests, operational amplifier is a generic multi-purpose amplifier that can be used to do a variety of functions. Now, it could be adder, subtractor, amplifier, differentiator, integrator. So all sorts of mathematical operations we should be able to do using this operational amplifier. So initially, when we were building transistor level amplifiers, then it was difficult to make large circuits with these transistor level amplifiers. So then now there is this operational amplifier as a black box that you could purchase, and that could be done by different companies, and they would be pin compatible, and using that operational amplifier you can create many circuits. So operational amplifier is kind of like as I like to call it, a sub-circuit which contains whole bunch of transistors, and it behaves in certain way. And that operational amplifier you can plug into different circuits to create different functions. So in this part of the lecture, we will discuss operational amplifiers in detail as a black box. So let's get started. So let's look at what I'm going to do is I'm going to take you to a website first, a commercial website, and let's look for a really famous operational amplifier which has been used in many applications. The name of the amplifier is 741. And this amplifier was designed by David Fulager in 1968 when he was at Fairchild Semiconductors, and then he moved on to Intercell, and finally he founded a company called Maxim. Now this particular amplifier is being used in so many applications purely because of its performance and really simple way to use it. So let's explore that amplifier online first. So here is I just typed up LM741, and this one is from Texas Instruments. Now many times these chips are also called like a jelly bean chips, which means that they are like a fundamental components which can be used to put together a whole bunch of other circuits along with it to create complex circuits. And using these operational amplifiers, your design becomes, the process of doing a design becomes very simple. So this LM741 amplifier, you can look at the website, and this is something called a product brief or technical document for that particular amplifier. So this you can, if you go online, and this is one of the configuration where this amplifier can be used. And as I said, this the LM740 from the triangle that we talked about is what we're going to study today. Not just LM741, but we're going to talk about a generic operational amplifier. And here you can see there is a positive supply, there is a negative supply, and we're going to talk about that. So this amplifier generally comes in different packages. So there is a like a circular package, LMC package, or it can be like a rectangular chip package. And then if you look at the package, it will tell you which pin corresponds to which terminal on the operation amplifier. Then there are absolute maximum ratings which are specified, so you should never exceed those, otherwise the manufacturer will not guarantee the working of the amplifier. I mean, you can cause damage to the amplifier and they will not replace it. So so those things you need to follow. Also, there is like a whole bunch of electrical characteristics, which is like a performance of the amplifier, minimum and maximum number, they are specified, the electrical characteristics are specified. So we are going to talk about all these things. How do you read all that stuff and understand what is the implication of each one of them. And you should be able to, once you understand the limitations or non-idealities of operation amplifier, which we will do in a follow-up lecture, you will be able to make a different, depending on the application, you can choose different types of amplifier, operation amplifier. Now this particular diagram shows, so this amplifier is created using BJTs, bipolar junction transistors, and you can see there are NMOSs, you can see there are NPN and PNP transistors and resistors and some capacitors in this particular amplifier. Once the amplifier is done, then you don't have to go inside the amplifier, because it will behave as a black box, as a model, the same way every time it's being used. Then there is a waveforms when the amplifier is being is used. It shows, and then generally there is some kind of layout example that is specified. Now in this particular case, just wanted to bring it to your attention. The rectangle with a semicircular cut is actually the chip package part of this amplifier, and if you see that black dot, that represents pin number 1. So that uniquely represents pin number 1, so that you don't flip it around and make a mistake. Okay, so and that way, once you have an example PCB layout, you can put this amplifier on top there. All right. And there are mechanical specification of the amplifier, how this is going to look like, so that you know how to mount this amplifier on a PCB. Okay, that's it. So as I said earlier, operational amplifier is a multi-purpose amplifier. And it can perform various operations. Such as adder, subtractor, amplifier, or you can do differentiator, integrator, etc. Okay, so when you buy the amplifier, it may look something like this. I'm just going to quickly draw the 3D picture of the amplifier so that you can visualize it, and then something like this, and then you will have few pins coming out. So in this case, there are totally 8 pins, and these 8 pins will be these are the ones which you, pieces of metal which you will solder down on the board. So you will have some on the other side too. Okay, so you get kind of visualize this whole thing. And then generally there is a dot over here, that means this is pin number 1, 2, 3, 4, and then it goes this way, 5, 6, 7, 8. Okay, so that's a generic convention. And in this particular case, we were talking about LM741 amplifier. So it's wired like this. So there is a triangle which is showing the amplifier. It has two inputs, positive input and negative input, that is connected like this. Maybe I should use a different color so it's easy to see. So let's use yellow for this. So positive input is connected to this one, negative input is connected to this one, and then the output is connected to pin number 6. Okay, and then we have, I'm going to use red color for supply connections. So pin number 7 is connected to your, I think it's VDD, and pin number 4 is connected to your ground. Okay, so that's what it looks like. So now, so this is the way, if you buy this particular amplifier, probably few cents or a few rupees, you will get it out there. Next time you come back to our lab, you can also, open it up and check it out in the lab, how it looks like. All right. So when we are doing circuits with it, this is the way it's going to look like. So we will draw the circuit like this. Okay. So you will have plus, minus, and then you will have supplies. Okay, so this is called VCC, VEE, and this is your output, V output, and generally I like to call this is VP and VN. However, different people name them differently. That's okay. One question that I would like to pose to you is, why is this called VCC and why is this called VEE? Okay, and sometimes you also see VDD and VSS. Okay, so let me explain that to you, because that could be a really simple interview question, and it's something that you should know if you're a circuit designer. Okay, so when we use bipolar transistors, okay, in any circuit, then you have a collector and emitter. So generally the collector terminal goes to the highest supply and or towards the highest supply, and the emitter terminal goes towards the most negative supply. Hence the positive supply is referred to as VCC in a bipolar circuit, and negative supply is referred to as VEE. Okay, and similarly if you are using a MOSFET transistor, okay, so let's say this is an NMOS transistor, then you have a drain region and you have a source terminal. So drain and source, and this is your gate. On this side, this is the base of the transistor. Okay, so generally the drain goes to the most positive supply. So you will, we call for CMOS circuits, generally the supply is defined as VDD, and the most negative supply is referred to as VSS. Okay, just a trivia that you should know, and this you will see it in many places. If the circuit is made using BJTs, then you will see VCC and VE. If the circuit is made using MOSFETs, then it's VDD and VSS. It's just a naming convention. VDD represents the most positive voltage, VSS represents the most negative voltage applied. Okay. Now, one more note about VCC and VEE and ground, okay, and analog ground, because there are so many questions about analog ground that are there in your mind, right? So there is no such thing that is physically identifiable analog ground. Analog ground is for our ease of understanding. Okay, so let me take an example over here. So if you look at the 741, I think it goes, you can apply plus 10 volts or minus 10 volts. Okay, but you could take an amplifier. Okay, and let's say suppose this is supposed to be plus 5 volts and this is supposed to be minus 5 volts. Okay, so this is your VCC and this is your VEE. Okay, so naturally what this means is that the signals which are being handled by the amplifier, they are going to be between these two ranges. Okay, and a convenient ground for this particular amplifier will be a 0 volts. Okay, so 0 volts, we can call that as ground or analog ground. Okay, now when we say analog ground, that means all your signals are around this particular voltage. So in this particular case, it turns out to be 0 volts is the analog ground, because let's say this is the output, and let's say this is 0 volts, then the signal which is going up and down, it can go up to plus 5 volts and minus 5 volts, purely because that's the way the supply voltage is given for this amplifier. However, let's take another example, which is most commonly used nowadays. Nowadays, you don't use dual supplies, you just use single supply, and in that case, so when you look at the instrument, okay, so this is your instrument which is providing you, let's say, let's take the latest, let's pick a number, let's pick 1.8 volts as our supply. Okay, so then you will see plus and minus. Okay, and then there will be chassis ground, which will be like this. So typically what we do is we short these two, and this and this, and here on the display you will see 1.8 volts. Okay, so this is what you will apply to your amplifier. Okay, something like this and something like this. Okay, so the chassis ground, which is where this particular instrument's ground is connected to the earth as a reference potential, is 0 volts here. Okay, physically 0 volts. Now when we apply this to the amplifier, now this is 1.8 volts and this is 0 volts. Okay, from this instrument point of view. However, when we look at the signals, we cannot really apply a signal with respect to this 0 volts. Okay, because what will happen is, if I apply the signal with respect to 0 volts, then if I apply input of, let's say, 100 millivolts at the input, then my negative going peak will be minus 100 millivolts. Okay, so this amplifier will not be able to process. So that's the reason we use something called analog ground. And analog ground is something like a reference in our head that we use all the time. Okay, so in this particular case, we could say that, hey, let's define VDD divided by 2, which would be 0.9 volts. Okay, and that would be our analog ground. Okay, what analog ground or AC ground, or also called AC ground, okay, is the signal is moving up and down around this analog ground signal. Okay, so you can put 0 volts here and 1.8 volts here, and whatever signals we are applying at the input and whatever we are seeing at the output, they will be reference to this 0.9 volts. Okay, and we call that 0.9 volts for our reference as a analog ground or AC ground. Okay, all right. So this will we will be dealing with this many times, and it will slowly become clear to you when we do the circuits. Okay, all right. So let's move on to our ideal op-amp. Let's talk about ideal op-amp. What are the characteristics of ideal op-amp? So every time we don't call it operational amplifier, we shorten and we call it affectionately op-amp. Okay, so ideal op-amp has we show it with a triangle. Okay, it has one input, second input. So this would be your this is Vn, negative input, this is your Vp, and then this is your Vout. Okay, all right. So negative input is called inverting input. Okay, positive input is non-inverting input. And of course, there is voltage gain between the two, and the voltage gain we specified as AV. Okay, this is your voltage gain. And if you look at the model of this amplifier, let me draw the picture for you here. So what we would see is, we would see we would model it like this. So this would be AV times Vp minus Vn. All right. So that's pretty much what it is. The amplifier, behaves like this. And what we are doing here is if you look at this particular term, we are taking a difference between the two terms. Okay, and that's why it's also called difference amplifier. All right. Now let me, when we talk about difference amplifier, let me ask you, let me give you an example of why are we really trying to take a difference between the two signals. Why don't we just amplify one signal and then amplify another signal and do something else and subtract them out, right? A good example that you can that I can give you to understand this is an ECG example, or something like any kind of measurement that you do on your body, for example. Okay, so in that particular case, let's say an ECG. I mean, I'm overly simplifying everything for you for the purpose of understanding. But ECG, in when you're measuring your heart rhythm or something like that, you're actually taking a difference between the electrical impulses at two different positions in the body. Okay, so for example, let's say this is your heart, and then this is your leg. Okay, so somewhere close to the leg. So I want to take this difference, and I want to take this one. I would like to amplify the difference between these two. So let's say we just did one amplifier like this and one amplifier like this. Okay, and then we said, okay, I will now take a difference between these two by adding another plus minus subtractor and something like this. So this example would illustrate this difference amplifier functionality of the OpAmp. So the signal, let's say we connect one lead towards the heart and one lead towards your leg, let's say. So if you, I'm sure all of you have played with an oscilloscope before, and I'm sure you have touched the lead of the oscilloscope. So if you touch the lead of the oscilloscope, you will see there'll be like a really large signal that's going on like this, right? And if you keep playing with the oscilloscope, you will see a 50 hertz type of tone, or a 60 hertz type of tone, depending upon which country you are in. So that and that's a pretty large signal that you will see that's there riding in your body all the time, okay, because the surrounding you are in. Now, the kind of signals we are trying to detect, for example, between heart and your leg, for example, to do an ECG would be really small signal, so which could be less than a millivolt. And here is something like 50 to 100 millivolts of 50 hertz hum, we call it, or that's riding on each side. So let's say there is a 50 hertz tone here, and there is a 50 hertz tone over here. Okay, so these are large signals, okay, which are large and noisy signals which are on each lead. Now, if we amplify them separately, then our desired signal which is going on is a small signal that's riding on top of this signal. And so when we want to amplify, we have to amplify both sides. So we want to make sure that this particular amplifier and this particular amplifier has a very large dynamic range. So it should be able to handle the small signal as well as the really large signal that comes along with each lead, right? So this is very inefficient. So instead, if we have a difference amplifier that we just talked about, which can do something like this here, Vp minus Va, and then we can simply take these two leads, and then we can use an operational amplifier type of circuit, and we can subtract them out right at the input itself, so that the common mode signal, as I like to call it, because this is a common signal to both sides, does not get amplified by the amplifier, and only the difference between the two signals, Vp and Vn, gets amplified. Okay, so what we would like to see in the ideal amplifier is we have differential input, okay, and then in this particular case we have single ended output, okay. So differential input means the amplifier will process difference between these two signals, these two leads, for example Vp and Vn. And single-ended output is just single output in this particular case, and this output will be reference to some ground, okay. All right. Now, what is the other feature that we desire is we desire infinite input impedance. Input in this particular case, let's call it input resistance. Okay. We will talk about impedance later stage in the course, but for now let's just say it's infinite input resistance. What infinite input resistance means that there is no current flowing inside the amplifier. Okay, so the amplifier does not load the previous circuit. There is no so it behaves almost like an open circuit. Okay, when it comes to any kind of current flowing into the amplifier. All right. The other thing we want is we want zero output resistance. So what this means is when you have this particular output AV times Vp minus Vn, and let's say there is some output resistance, right, R out. We want this output resistance to be zero. Okay, the reason for that is if I have some impedance connected over here, some resistance connected over here, we don't want this voltage divider effect. We want this entire AV Vp minus Vn to appear at the output, okay, in the simplest terms. I'm going to use a new term now and I'm going to explain it to you. We call it common mode gain. Okay. So what does common mode gain mean? What does common mode signal mean? Common mode means something that's common to both the terminals. Okay, so we are looking for any signal that's common in both Vp terminal and Vn terminal, and that's what we call it common mode voltage. Okay, so we don't want to amplify any voltage which is applied to both Vp and Vn. Okay, a common mode voltage. So for example, in our case, the previous example case, here we were applying we were applying to this amplifier the common mode like a AC signal, which is due to our power supply or electrical transmissions, which is 50 hertz, let's say, and that would be really large. And that would be same on both sides, right? Because it wouldn't change much from one place to another place in the body, and we don't want to amplify that signal. Okay, so the amplifier should reject any kind of common mode signal which exists on both sides of the both terminals, Vp as well as Vn. And what we would really like to do is then so the point is we want zero common mode gain. The common mode gain should be zero, and of course we want infinite differential gain. So we want AV, which is a differential gain, we want that to be as large as possible, infinite for that matter. Okay. Other thing we also want is we would like the bandwidth, which we will talk at later point in the course, should be infinite, meaning you want it as large as possible. So if you apply 1 hertz versus if you apply 1 megahertz or 100 megahertz signal, then the amplifier should be able to handle all that. But this is our wish list for an ideal amplifier. Okay, in reality we get different things, and then we try to deal with, we try to understand, estimate, and then we try to deal with them in our circuits. All right. So let's do a transfer characteristics of the amplifier. Okay, so in this particular case, let me draw the amplifier first. Again, minus plus, And in this particular case, let's just say this is your Vn and this is your Vp, okay, and this is V out. Okay, so I'm applying some common mode signal and some differential signal. So how would we describe that when it comes to using actual voltage sources? Okay, so follow my train of thought. So let's say I would like to apply a differential signal of let's say VID. Let's say I would like to apply differential signal of VID to this amplifier. Then what we can do is, hey, that's pretty easy. I can just draw a voltage source that looks like this, okay, and that would be my VID. Okay, so we know the difference between Vp minus Vn is VID. So, however, we don't know what actual voltage Vp is or Vn is, or like what is it reference to. So we only know difference between Vp and Vn. So then what we do is, let me redraw the circuit to make a point. So I can also do something like this. So this would be minus again and plus again. So then I'm going to break that voltage source in two pieces first. Okay. And then I'm going to say, hey, let me just make this VID by 2. This is also VID by 2. So same thing, right? You can say apply plus minus plus minus. So I just broke that voltage source in two pieces with VID by 2, and this center point is my common mode potential for the amplifier. So here I can put in something called, let's call it VICM plus minus. Now let's figure out using KVL what's the potential at Vn and what's the potential at Vp. So Vn will be equal to VICM minus VID by 2, and Vp will be equal to VICM plus VID divided by 2. Alright, so this is the way we define the input voltages to the amplifier, and then you will have a V out that will be again, you have a VDD in this case. I'm just giving an example, and let's call this ground or 0 volts, and we apply VDD, and then we can say that the V out is going to be between ground and VDD. Alright, so if we plot these characteristics, how is it going to look like? Okay, so let's first plot the characteristics of the amplifier, and we know that the amplifier has a very large gain AV. Okay, let's do a simple plot first. So where I'm just plotting VID, okay, and this is my V output first. So what would be the output voltage lie between? The output voltage will lie between VDD and ground. Ground here we are saying that's equal to 0 volts. Okay, so I'm going to, for the sake of discussion, I'm going to call this as 0, and this will be my VDD. Okay, so if I apply VID, then we can call this center point, which is VDD divided by 2, as our analog ground. Okay, around which the output can be. Okay, so in this particular case, we can say that if the VID goes up, then this is what the characteristics will look like. Something like this. Okay, so if VID goes positive, then the output of the amplifier will go positive, and then because the gain is large, as soon as VID goes beyond few millivolts, the amplifier output will clip to VDD. Okay, and the slope of this line is the gain of the amplifier, AV. And as I said again, this AV, we would like it to be very large. It could be 1,000, 10,000, 1 million, something like that. Okay, so the higher the gain, more ideal the op-amp will look like. All right. So once you understand this, we can also, for sake of illustration, I would like to plot this transfer characteristics as a function of what do we see at Vp and Vn, because in this particular case I'm plotting with respect to Vid, and so it's also important to understand how the transfer characteristics look like when we just plot Vp and Vn also. Okay, so in that case, let's draw it here differently. I'll use a different color. All right, so this is going to be I'm going to plot Vp, which is equal to Vicm plus Vid divided by 2. Okay, and this is our output, Vout, and output also will have some common mode voltage, which is what we are calling analog ground. In this particular case, if our VDD is right here, then we are saying that at output I have VDD divided by 2. That's where my output is. Okay, so I want you to think about it for a second, and then tell me how the transfer characteristics will look like if Vicm is over here, let's say. Okay, so I'll give you 10 seconds or so and plot the characteristics. And note, I'm showing Vp over here. Okay, so Vp is given by Vicm plus Vid by 2. So hopefully you were able to figure out how the transfer characteristics is going to look like. So what we are going to do is we are just going to draw some few things here as a reference for you, so that okay. Now when Vp goes positive, okay, we expect the amplifier to amplify the voltage quickly. Anytime Vp goes positive, so we expect if Vp goes positive compared to Vicm, then we expect the amplifier to show a characteristic something like this. Something like this. Okay, and even though it doesn't look like a straight line, it should pretty much look like a straight line like this over here. Okay, all right. So let's discuss a role of the Vicm, and what does Vicm do in this particular case. Okay, so as I said earlier, we would like to have zero common mode gain, which means that if Vicm changes, we don't want output to get affected. Okay, so that's the key point I'm trying to make here. So let's say we used a different value of Vicm volts. Let's say we changed the Vicm from, in this particular case, let's say it was VDD by 2, and now we moved it to maybe 3 VDD by 4, something like that. So now this particular voltage will be somewhere over here. Then can you stretch your imagination and draw the characteristics of this amplifier? What would you see? So I will just quickly draw it for you. What you would expect to see then is something that will look like this, something like this, and this is your new Vicm. So this would be 3 VDD divided by 4, and what you would see is as the Vp goes around that voltage, you will see the op-amp respond, and the output is still VDD by 2, because that's where the output is referenced. Okay, and in case we choose different Vicm value over here, so which would be let's say VDD divided by 4, then also you would see transfer characteristics that would look something like this. Okay, let me redo that. Something like this. So for some of you it might be a little bit confusing in the beginning, but what I'm trying to explain to you is we are plotting voltage at Vp, which is Vicm plus Vid by 2. Now when you do that, as the Vp, when Vicm is fixed, that means the Vid is the one that is changing. Okay, and what finally matters is the differential voltage between the two terminals, and and what we are desiring is this particular characteristics, which is VID, and then this is your V out, and we desire this particular type of characteristics, and something like this, and this characteristic should be independent of VICM. That's what the op-amp does. And this VICM is the one that I explained to you a while ago. That's like a common mode signal, which is there on both sides when you're doing this ECG example. Okay, and what we are trying to identify is not the common mode amplify the common mode signal, but is the difference between the two. So, for example, to give you a little bit visual imagination of how this signal is going to look like, is let's say we have this is our 50 hertz, something like this. So this is on VP and this is on VN, and riding on top of this would be your signal that we desire. So then that signal would be something like this here, something like this here, let's say, and then would be something like this here, something like this here. Again, I'm exaggerating substantially, and then on this side it will be on the opposite side. Something like this. Okay, so as you can see, the common mode, the green part is same to VP and VN. However, the red part, which is what we are most interested in, is going in the opposite direction on VP and VN, and that's the signal we are trying to amplify. So when we feed this into our op-amp based circuit differential amplifier, then what we desire at the output would be something like this. So which would I'm just going to draw the something like this, right? So you will see something that will go like this, something like this. And we amplified the weak differential signal. However, we did not respond to any one of these, the green common mode signal. Okay, so that's in a nutshell how I can explain to you the common mode signal versus differential signal. Okay. Now let's get into a little more details about how do we use this amplifier. Okay, so different circuits that we're going to attempt to do with the amplifier. So the first one is let's take the simplest example. So here is a triangle which is representing the amplifier plus and minus, right? So if we connect this and this is reference to ground here, and if I connect the negative terminal to ground, again here whenever I show these ground signals, they are all analog ground related signal. Okay, because they are some voltage which are between 0 and VDD, the supply voltage of the amplifier, and this is implicit assumptions going forward throughout the course. So you should never confuse this with like a absolute zero of the amplifier. Okay, so this is a analog ground, and now I'm applying a positive signal here, which is, let's say, VP. What do we expect at the output? So whenever what we would expect is when VP is equal to 0, just like Vn, okay, we would expect 0. Okay, and this is our VP and this is our V out. And then if the Vp goes up compared to Vn, then we would expect things to go positive, right? So this is what we expect. Pretty straightforward. Something that looks like this. And this slope of this curve would be your AV. All right. Similarly, we can do a flip case where we would apply a, let's say, let's use a different color, and I would apply a, I would change the input structure here. So here in this case, I'm going to apply analog ground to Vp, and then I'm going to apply a plus minus input source here, Vn. Okay. Then what do I expect? Then what we would see is something that would look like this, right? Something that would look like this. So this would be for the Vn case. So the red would be Vn case. So whenever Vn is negative compared to Vp, then output will go high. And when Vn becomes positive compared to Vp, then the output will go low. Okay, so this is kind of important to understand. So whenever you apply input to the non-inverting terminal or positive terminal, then the output output of the amplifier should go positive when you apply relatively positive input to the non-inverting terminal as compared to the inverting terminal. So this is pretty straightforward, and you should just kind of one thing that I would like you to do as students is I'm doing all these things in the classroom, and you're probably watching the lecture, but I would strongly recommend all of you to have a notebook and draw all these pictures, because circuit design is visual. You draw, and then once you draw the schematics, then it will really sink in. If you just look, at that time it will appear like you are getting everything, but unless you draw it without looking, the ideas will not sink in. So it's really important to draw the pictures, and you will see why I'm saying that, because of the next particular example I'm going to show you. Okay, so let's take our amplifier, right? What is the equation of the amplifier that we would like to use? So equation of the amplifier is V out equal to AV, which is large gain, times Vp minus Vn. Okay, so now I'm going to give you a schematic, very simple schematic I would like you to draw on a piece of paper, and then can you solve the what would be the output. Okay, so what I'm going to do is I'm going to apply a voltage V in over here, V in, and then I'm going to connect it in something like a unity gain feedback type of network that you may have seen, and then I'm going to ask you to write an expression for V out. Okay, I'll give you 10 seconds to write, and then I will start writing the question, writing the answer. Okay, so as I said again, we will start from this expression, and then I will just substitute the terms for these two terminals, and then what we would get is V out is equal to AV times, what is V positive voltage is also V out, minus Vn. What is Vn? Vn is V input. Okay, and then we can let's see, we can say AV times V in is equal to AV minus 1 times V out. So then we can say that V out divided by V in is equal to, what is that equal to? That is going to be equal to AV divided by AV minus 1. So this, since AV is really large number, you can say that, hey, that's pretty close to 1, right? So if I apply input voltage, I should see an output voltage equal to the input voltage. So if you have gotten the same answer as I have shown, then I'm going to tell you that it's actually a trick question. It's a trick interview question. In reality, the circuit really doesn't behave this way. So I'm intentionally misleading you on this path to see, how you can you can fool yourself, okay, for that matter. So let's see what is really going on. Let's think about this for a minute. Okay, let's say that the gain AV is 1 million. Okay, 1 million dollars, which means there are 6 zeros, right? 1 million. AV is equal to 1 million. Okay, all right. Now, let's say in this particular case, the supply voltage is 5 volts and 0 volts. And as I said, we will apply input voltage, which is equal to 2.5 volts for a minute. All right. So since AV is very large, that means somehow we are able to get output equal to 2.5 volts approximately. All right. So if output is 2.5 volts, then the difference between the two sides is going to be very small, right? I mean, 0. So as a result of which this one looks fine. However, what I would like you to think about is, let's say this 2.5 volts input voltage, we just take it slightly higher. Let's say we take it higher by 1 millivolt for that matter. Okay, so if I take it up by 1 millivolt, then this input voltage will be 2.501 volts. All right, I'm just lifting it up by 1 millivolt. Now what will happen? Think about it. I am taking a negative terminal of the operational amplifier and I'm taking it positive compared to a non-inverting terminal. So suddenly my difference between the two is only 1 millivolt, and it's going to get amplified by the gain of the amplifier. And what do we see at the output? Which way will the output voltage go? Now that's something that I would like you to think about. So would the output voltage go high or low? If you have answered low, then that's not correct, because we are taking negative input and we are raising it positive compared to the other input. So what we expect, whenever we touch the negative input and take it higher compared to positive input, the output is supposed to go low. So since the gain is so high, what will happen is this 2.5 volts will suddenly go to 0 volts. Okay, because the gain is so high. Now, so the key point I'm trying to tell you is, the amplifier is not really behaving like this. This equation that we have brought out, because in this particular equation we just proved ourselves that amplifier is actually unity gain amplifier. Basically, V out is equal to Vn, but that's not what is going on. And the reason for that is something called feedback. This feedback part we are going to discuss at length in future lectures, but there are two types of feedbacks. Okay, there is a positive feedback and a negative feedback, and negative feedback is something I'm sure you have experienced it all the time. How you do in the exam, and your parents will give you some feedback, right? And generally it's a hopefully feedback which will improve the situation, right? So in this particular case, if you look, the feedback is actually positive. What that means is, if for some reason the input is going up, then the feedback will make the situation even worse. Okay, so it will amplify and make the difference between positive and negative terminal go in the same direction. So another example of a positive feedback that you can imagine is many times you go for a concert or some kind of program, and then the person who has a microphone goes very close to the speakers. So in that case, what's going on is, whatever you speak inside the microphone is going through the microphone, is getting amplified, coming out of speakers, and from speakers again it's going back into the microphone. And when something like this happens, and the two signals are going together, then we will get something called positive feedback. And the positive feedback generally in the amplification type of situation is not a good thing, because it would latch up the system one way or the other. And in the amplifier case, you will hear the speaker microphone case example that I gave you. It will latch up. It won't latch up. You will just hear a really loud tone, which is kind of the other mode of operation of the amplifier, which is like an oscillator. Okay, we are going to touch up on that later on. Coming back to this particular example, this is an example of a positive feedback. Okay, so watch out for feedback before you start analyzing the circuits, because you may fool yourself. You may assume that the circuit will behave in certain way, only to find out that the positive feedback will spoil the party. Okay, so to have a negative feedback, you would draw the circuit in this fashion. So the classic example would be something like this. So you have positive input, negative input, and this is again V out, which we call it positive output. So this we need it to go over here. So we can see now we have a negative feedback in this particular loop. In the earlier case, we had if you look at this particular loop, feedback loop, it's positive feedback. There is a positive sign. So here, if you look at this particular loop, there is a negative feedback. So in this particular case, what will happen? Let's take an example, right? Let's say same example, this is 2.5 volts and output is also 2.5 volts, so that there is no difference between the two terminals. And now if V out goes positive, okay, let's say this goes up by 1 millivolt. So this becomes 2.501 volt. Okay, so here in this case the positive input is going positive, which means the output will also follow, and here this will also become 2.501 millivolts approximately. Okay, so you can see now, since this went up along with it, the difference between the two terminals VP and VN still stayed 0 or close to 0, and as a result of which this circuit is in a stable operating point. Okay, so let's solve the equation for this one. I'll give you another minute, not minute, 10 seconds to solve. It should be pretty straightforward. So V out is equal to AV times VP minus VN, and in this case we can substitute VP, which is, what is VP, is V in, and Vn is equal to V out. Okay, and you can quickly prove it to yourself that V out over V in is going to be equal to AV divided by 1 plus AV. And that's, if AV is large, and that's the reason we say all the time that voltage gain of the amplifier has to be, operational amplifier has to be large, so that this number comes out to be almost equal to 1, okay, when AV is large. Great. Okay, so in the next part of the lecture, we are going to go through a few more examples of circuits with operational amplifier.